Hey everyone, and welcome. Have you ever just stopped and wondered what a massive supercomputer, the phone that's right there in your pocket, and even a simple calculator all have in common? Well, it's this incredibly simple, really elegant idea. Our entire unbelievably complex digital world is built from just one or two types of a single fundamental component. So, here's our game plan for today. We're going to start with those tiny building blocks. Then we'll see why they're the gold standard. After that, we'll look at how they actually do the math. And then, this is the cool part, how they somehow learn to remember things. And finally, we'll see how it all scales up to run, well, everything. All right, so let's just dive right in at the very beginning. In this first part, we're going to pull back the curtain and meet these humble heroes of modern technology. I mean, really, think about it for a second. You look at a modern processor with all its insane complexity, what could possibly be the one single unifying thing that makes it all tick? Well, the answer is this: the universal logic gate. It's a simple concept, but it is literally the key that unlocks everything digital that we use every day. So let's take a closer look at what that actually means. So what makes a gate universal? Well, it means you can take just one type of this gate, and by wiring them together in different ways, you can build any other kind of logic you can dream up. An AND gate, an OR gate, you name it. You don't need any other parts, just this one. And here they are, the two stars of our show. The NAND gate, which is just an AND gate with its output inverted, and the NOR gate, which is an OR gate with its output inverted. You should really think of these as our standardized digital Lego bricks. Everything, absolutely everything, is built from these. But why these two? I mean, out of all the possible logic gates, why did NAND and NOR become the industry standard? Well, it all comes down to some very cold, hard, practical reasons. You have to remember, in the world of computer chips, you've got billions of these things crammed into a tiny space. So every little advantage adds up. It turns out universal gates are physically faster, and they're cheaper to make. Now, when you multiply that tiny, tiny advantage in speed and cost by a few billion, suddenly you've got massive gains. And that's really the key takeaway here. If you standardize on just one type of brick, the whole design and manufacturing process becomes way, way simpler. You're not juggling a whole toolbox of different parts, you're just using one over and over again. And that leads to incredibly efficient design. All right, let's keep building on this. Now we're going to get to the core of what a computer actually does: computation. How do these simple little bricks create the logic that does math at, lightning speed? So there's this really important rule in digital design. The absolute fastest way you can build any logic circuit, doesn't matter how complicated, is with a structure that only has two layers of gates. If you add any more layers, you're just adding delays. And in computing, speed is everything. And this is where it all just clicks together so perfectly. You see, those ideals, super fast, two-level circuits, they have technical names like sum of products. And it just so happens that you can build them entirely using only NAND gates. The other form, you can build it entirely with NOR gates. It's a perfect marriage. The fastest, cheapest gates are the perfect tools to build the fastest possible circuits. And you see this in practice everywhere. Take a decoder, for example. Think of it like an address book for your computer's memory. It helps find the right spot. Well, those are almost always built exclusively with NAND gates. They're designed for something called active low operation, which is just a standard where a 0 signal turns something on, not a 1. And NAND gates are just perfect for that. All right, now for something that, well, it sounds like it shouldn't even be possible. We've been talking about gates making decisions, right? Performing logic. But how on earth can these simple components that just react to what you give them be used to store information, to create memory? It feels like a total paradox, doesn't it? A gate's output is supposed to change the instant its input changes. So how can it possibly hold on to a value after the input is gone? Well, the secret is all in some very clever wiring. So check this out. It starts with this beautiful little circuit called the SR latch. You take two of our NAND gates, and you feed the output of the first one into an input of the second one, and you feed the output of the second one back into an input of the first. This cross-coupled feedback loop, that's the magic trick. It creates a stable state. It allows the circuit to latch on to a value and just hold it. And just like that, you have a 1-bit memory cell. And it works just like a simple switch. You send a quick low signal to the set input, and boom, the latch stores a 1.
You send a low signal to the reset input, it stores a 0. And if you don't send it any signal, that feedback loop just takes over, and the circuit holds on tight to whatever value it had last. It remembers.
And look, this isn't just some neat theory from a textbook. This exact principle is the foundation for the memory inside your devices right now. The super-fast SRAM inside your computer's processor, it's built from circuits just like this. And the very name of the flash memory in your phone or your SSD, NAND flash or NOR flash, that comes directly from the universal gates that make them work.
Okay, so for our final section, let's pull the camera all the way back and see how these humble little bricks scale up to create the absolutely incredible processing power we all rely on every single day.
It all starts at the bottom, at the most basic level. You have millions, no, billions of tiny electronic switches called transistors. And these transistors are simply arranged to create our universal NAND and NOR gates. Okay, then you take those gates and you start combining them, just like Lego bricks, into bigger, more specialized units. You build things like adders for doing math, multiplexers for choosing between different data streams, and those decoders we talked about earlier. Each one of them built from nothing but our universal gates.
And then you put those pieces together, and what do you get? You get the very heart, the very brain of a processor, the arithmetic logic unit, or the ALU. This is the part of the chip that does all the real work, all the calculations, all the decisions, and it is made from the ground up out of our simple bricks.
I love this analogy because it just hits the nail on the head. If you think of a digital system as a giant building, then universal gates are like your two standard types of brick. They're incredibly cheap, they're incredibly strong, and you can build absolutely everything with them. The foundation, the walls, the roof, the whole thing. It's just such a powerful idea, isn't it? That all of this immense complexity can grow out of such simple, elegant, universal rules. It really makes you wonder, as we start pushing into things like quantum computing and AI chips, what's the next fundamental brick going to be? What simple, elegant concept will be the foundation for everything that comes next?